Good morning, everyone. I hope you all are keeping well. So, as we have already started semester 2, so today I'm going to start the Nonparametric Statistics course unit. So by now I have already uploaded the module descriptor and lecture materials to Cal. So I think you all have access to Cal. So I want you to I want you to have a look on Cal, and then you can download all the lecture materials, and I'll be communicating all the important things using Cal. So you need to have a good touch with Cal, then it's easy if I'm planning to conduct an exam, an online quiz or something like that. I will inform you in advance through Cal, so you have to always keep in touch, right? Okay, so I think we can start today's session. Probably in most of the times I will be conducting this lecture series using recordings. So what you can do is you can just allocate, you can just keep the time slot which is allocated for this particular module in your timetable free. So then you can just take the recording and listen to that during that time period, right? And then you can raise questions. We'll be discussing some tutorials, and we'll be discussing some questions. When you have questions, we'll be discussing them in the question forums, right? So for them we will be taking one-to-one online sessions, right? Okay, so now I think we can start today's session. Non-parametric statistics. So the first question that I have to ask from you is, why do we use non-parametric statistics? Now in statistics all the time we say there are two branches in statistics as parametric and non-parametric, and then parametric methods are more accurate, they have high accuracy. If all these things are true, then why do we use non-parametric statistics, right? So one thing is why we use non-parametric statistics is, when we are failed to use the parametric methods, we have to always go with the non-parametric statistics. Okay, I'll explain that to you using an example. So let's say you have x1, x2, x3 up to xn. This is a random sample which is coming from some population, and you want to make an inference about the population mean. So if you can recall the things that you have learned in inference, right? So what you have to do is you have to first write down your null hypothesis and the alternative hypothesis. So in this case, let's say we want to test whether the population mean value is equal to a given value mu naught, right? In that case, you can write the H naught as mu equal mu naught, and where your alternative as mu not equal mu naught. Alright, so in this case, what you can do is, if we know the population is coming from a normal distribution, we have no problem. Only thing we have to check is whether we know the population variance or not. Now in this case, they have not given any information about the population variance. So if you know that the population is coming from a normal distribution, we are going for the t-test. So this is the t-test statistic. You can see that is x bar minus mu naught over s over root n. So what we do is we calculate the test statistic using our values, the sample data, and then if you we can reject h naught for too large or too small values of the test statistic. Right, so actually we can apply these parametric methods when we are testing for mean values under two conditions. One is if you know that the sampling distribution is having the population is coming from a normal distribution, and if you have no idea about the population variance, we are going for the t-test. And if the sample is coming from a normal distribution and if you know the population variance, you can go for the z-test. So that's what we do in parametric methods. So what happens now? Let's say if you have no idea about the sampling distribution, but your sample is very large. So in that case, we know we can always apply the central limit theorem, and then we can assume the normality, and then still you can apply the parametric methods. So in other cases, what will happen if the normal distribution is not appropriate, right? When you have a sample, if the normal distribution is not appropriate, if you can't even use the central limit theorem, one possible way to do is you can apply a transformation. Right? For an example, let's say we are going to apply the transformation y equal log x. So in this case, if after applying the transformation, if you can just apply the normality, then you can go with the normality. Then you can go with the parametric testings, right? But sometimes even when you apply the transformations, if still the distribution is not normal, then you have a problem, because if you have if your sample is too small, and even if you apply the transformation, even if you can't see a normal distribution, then there is a problem. What can we do? So we can't go for parametric methods. So that's where you have to use the non-parametric procedures, right? So in this case, as I told you, why we are using this non-parametric procedures. So the first situation is when you use the non-parametric procedures. Actually, when you compare the parametric and non-parametric methods, you will see in non-parametric methods we don't want to know about the population parameters. So when you are not involving the population parameters in your testing procedures, we always encourage you to use a non-parametric method, right? So there are valid reasons why you go for a non-parametric procedure, because we know when you compare that with parametric methods, it's not that accurate as parametric methods. So one thing is, if you have a sample, and in that sample, if you take the measurement scale of your variables, if it is in a weaker scale where you cannot apply the parametric methods, for an example, if you have count data, if you have rank data, then you have to apply the non-parametric methods. And also, if you recall the inference, what you have learned there, when you apply a particular parametric test, you have so many assumptions, right? So in that case, you have to check whether all the assumptions one by one, whether all are satisfying, right? So in such cases, if assumptions of the parametric tests are violating, then we can apply non-parametric methods for such scenarios. And also, if you want results quickly, and if you have no statistical software, if you have to do all the calculations manually, yes, you can apply non-parametric statistics. So in all these cases, you can apply the non-parametric statistics, right? So as in every case, when it comes to non-parametric procedures, you have pros and cons, right? So I'm going to discuss some of the advantages and disadvantages of the non-parametric methods. So one major advantage is we have very few assumptions. Now you will see when we are discussing the non-parametric procedures, we have very few assumptions compared to parametric methods. But even in those assumptions, you will see they are very easy to satisfy, right? So that is one of the major advantages, and also it has a wider scope. So since you have very fewer assumptions in non-parametric statistics, so you can apply it to anywhere. So you have a wider scope, right? And then we don't want the population parameters. We are not getting involved with the population parameters. So when it comes to parametric methods, sometimes we want to know about the population mean, sometimes the difference between two means. But when it comes to non-parametric methods, we are not involving any of the population parameters. So even if you have no idea about the population parameters, we can apply these methods. So the chance of they are being improperly used is small. Why? So I told you we have very fewer assumptions in non-parametric methods. So if you have very fewer assumptions, you have a very small chance to use a particular non-parametric procedure in an inappropriate manner, right? Because we can easily satisfy all the assumptions. When you have so many assumptions, sometimes we never know if you have violated one or two assumptions, we have still used that test. So actually that is wrong. So that thing will not happen when it comes to non-parametric statistics. And another thing is it's very applicable even the data is measured on a weak measurement scale. Right? So as I told you before, if you have count data, if you have rank data, you can still apply these non-parametric methods. And also it's very easy to understand. So when it comes to parametric procedures, if you don't have a good knowledge on statistics, sometimes it's hard to understand all the interpretations. But in this case, the non-parametric procedures, it's very, very easy to understand. Even if you have no knowledge about it, even if you have zero knowledge in statistics, right? So that's why we are using this non-parametric method, especially in the medical field. So you will see because you have very less number of data when it comes to medical researchers. So in those researchers, we always use this non-parametric methods, right? And and this is very easy to calculate, right? So its computations are very easy and quick. So that is also one of the advantages. And when it comes to disadvantages, one is sometimes we may lose some information. Because now, for an example, if you take the one sample sign test, we just take the difference and we just count the number of positives or count the number of negatives you have. So that is the only thing we are looking for when we are when we are performing the sign test, right? We don't care about other values in our data set. So in that case, sometimes we may we are wasting information in our sample. But when it comes to parametric, we use all the information. We are using all the parameters in the population. So in that sense, it's a disadvantage. And also sometimes it's difficult to calculate by hand when you have large samples, right? So as I told you, in most of the cases, we are doing all these calculations manually. So if you have large samples, it's a bit hard to do the calculations manually. And also when it comes to non-parametric statistics, now you will see when we started to do all these things, for each and every test, in most of the case, we have to refer for a table. Like in parametric, you are referring the Z table and T table. In non-parametric, you have to refer the binomial table, runs table, Wilcoxon table, likewise. But these tables are sometimes they are very long and also they are not widely used. So, or because of all these reasons, that is also becoming a disadvantage, right? So you can see there are advantages and disadvantages when it comes to non-parametric methods, right? So the next question is, now when we talk about parametric methods, most of the time when you want to use a central tendency measure in your population or in your population to make inferences, we used mean value of the population. But when it comes to the non-parametric methods, we are not using the mean value. Instead, we are using the median. So why? Why do you think that we are using the median instead of mean value? Right, so I'll explain that using this example. So you can see this sample of data, right? So you have 9 values, 1, 4, 5, 6, 10, 7, 8, 9, 2. So if I ask you to calculate the mean and the median for this simple sample, what you have to do is we take the summation of all numbers and divide by 9. So you'll get mean value as 5.78. And since you have 9 values here, 9 plus 1 divided by 2, that is the 5th observation. So in the 5th place, you have the median value as 6, right? So that is, you have the mean as 5.78 and median as 6. So in this case, what I'm going to do is I'm going to change 10, that is the maximum value of the sample, to 15, right? So if I ask you to calculate the mean and median again, you will see when you take the summation and divide by 9, the mean value is changing, that is equal to 6.33. But if you calculate the median, that will be still equal to 6. So the median is not changing, right? So now we can see, even though we change the values in our sample, mean value is changing but not the median. So actually the median is not changing due to extreme values of your distribution, right? So because of that we call it's a robust estimator for extreme distribution. So no matter what is the shape of our distribution, whether it's skewed one, whether it's a symmetric one, when you have extreme values, there is no effect for the median. So because of that, since we have no understanding about the population distribution, when we are applying the non-parametric statistics, we always use the median as our population parameter. Right? So if I just recall you what is the median, we know when you have a sample, median is just the value which is right in the middle of your data set. So in other words, if you take median as M, right, median as simple M, so the probability where a given value is less than to the median or a given value is greater than to the median is equal, that is equal to 0.5, because it's right in the middle of your data set. So when we are using this median as a parameter in non-parametric statistics, sometimes they use the notation mu also in some reference books, but I'll be using simple M to denote the median value of the population throughout this course. So it's up to you. You can use whatever the symbol you like, right? If you like to use mu, you can use it, because mu is not only for the mean. You can use in non-parametric procedures mu for median as well, right? So that is that is actually the basic understanding that you need to have why we are using the non-parametric methods and what are the advantages and what are the disadvantages and in what kind of situations you have to apply the non-parametric methods, right? And why we use the median as the population parameter in the non-parametric procedure. So I think that will be clear with y'all. Right? Okay, so I'm going to discuss a test that we are using in non-parametric methods. So that is known as the one sample sign test. So if you just Google this and if you go through with the reference books, you will see this is one of the oldest non-parametric methods. Right, so we are using the one sample sign test when you have to make inferences about the population median. Right, so in this case what you do is we take our data set and we calculate the difference. We check the difference between the observed value and the given median value and we count how many differences are positive and how many differences are negative. Right, so based on that we are going to perform the test. So I will do examples, you will then understand. Right, so when it comes to the one sample sign test, there are some assumptions that you have to make. So you can see the three assumptions here. So one assumption is the sample available for analysis is a random sample of independent measurements from a population with an unknown median m. Right? So what you have to do, when your sample should come from, your sample should be a random sample and it should come from a unknown population where all the sample values are independent, and also the variable of interest in your sample, it should be at least in ordinal scale, right? It can be interval or ratio, but it should be at least ordinal, not nominal. And also the variable of interest in your sample, it should be a continuous one. So you can see it's very easy to satisfy these assumptions. So if you can satisfy these assumptions, you can and if you are testing for the population median, you can go with the one sample sign test. So when it comes to one sample sign test, you can perform a one-side test or you can perform a two-side test using the sample value. So I'll explain one by one. Right, first let's see how to use one-side tests. Okay, so you will see in my lecture notes I have always kept you some spaces, that is for you to write down these things. You have to fill all these spaces by yourself. So when I'm doing the lecture, I will tell you what you have to write so you can fill those spaces, right? Okay, so when it comes to one-sided test, there are two options. Right, we know when you have a question, when you have an inference question, whether it's parametric or non-parametric, when you are setting the hypothesis, you have to read the question and you have to identify the claim, and we take the claim as our alternative hypothesis, right? So same thing you have to apply here. So when you are given with the question, you have to read it, and if you are asked to check whether the population median is less than for a given value, right? That is, your H1 is m is less than m naught, where m naught is the given value, right? For an example, let's say you want to check whether you need to check whether m is less than 10, right? You need to check whether m is less than 10, right? So here m naught is something like 10. Okay, here so you can use this one-sided test where your alternative is m less than m naught. So in that case, your null hypothesis, you can set it as m equal to m naught, your null hypothesis, or else if you would like to use the inequalities, you can use it as h naught as m greater than or equal to m naught. So you have both options. If you like to go with inequalities, you can use the right opposite of the alternative, that is m is greater than or equal to m naught, or else you can just write m is equal to m naught and we are testing m is less than m naught, right? So here when you are given with the one-sided test, so first you have to read the question and write down your test statistic in this way, right? So the next important thing is, what is your test statistic, right? So when it comes to the test statistic of this, we denote the test statistic by capital S. Right, we denote the test statistic by capital S, and that is equal to, I'll write it using equations. Your test statistic capital S is equal to n plus. Right, this is the general notation that we are using. So now you have a problem. What is this n plus? Your test statistic, we denote the test statistic using capital S, and that is equal to n plus. So what is this n plus? So n plus is the number of positive differences. Number of positive differences, that is n plus, right? So I will explain you when we are doing the example how to calculate or how to count the number of positive differences. So what you have to remember is, when it comes to the one-sided test where your alternative is m less than m naught, your test statistic is capital S, it is equal to n plus, where n plus is the number of positive differences, right? And then you have to calculate the p-value of the test, right? So when it comes to the p-value of the test, what happens here is, now when you check your hypothesis, you can see when h naught is true, the testing value of your population, that is the m naught, the population median is equal to m naught. So we know when you take your population, you have m naught right in the middle, right? So if you take, in such cases, if you take the probability where your test statistic, right, where your test statistic is less than this particular value, right, where your test statistic is less than this median value, right? And if you want to calculate the probability where your test statistic is greater than this median value, so there you have the same chance actually, because in these cases we can see you have the because the m naught is the population median, right, the testing value for the population median. So if even h naught is true, that is actually the population median. So if you check the number of positives, right, or the number of negatives. In the other case, your test statistic would be the number of negatives. So you have an equal chance to get equal number of positives and equal number of negatives. So in this case, probability where S is less than the checked value M naught, and the probability where your test statistic is greater than the checked value M naught, this should be equal, and that should be equal to 0.5. Right, so you can see that is when you pick any value from your distribution that is either less than or greater than your median value M naught. That should be right if it's the median. So in that case, you can see it shows the characteristics of a binomial distribution. When you take any value, it's either less than or greater than the median value. So in that case, and you have the 0.5 chance to as the probability to be greater than or less than to the median value. So you can see now this is having the characteristics of the binomial distribution. So when H naught is true, so these all are happening when H naught is true. So I'll write it here. So when H naught is true, when H naught is true, right, this probability is there. So because of that, we can say our test statistic is having a binomial distribution where n is the sample size and 0.5 is the probability of success. So based on this, we are going to calculate the p-value of this test statistic, p-value of this test. So when it comes to the p-value of this one-sided test, that is equal to the probability where your test statistic is less than or equal to S naught, right, where S naught is the observed value of your test statistic. So S naught is sometimes, it can be, I'll just zoom the font size. Right. So S naught is sometimes, it can be, now when it comes to this one-sided test, it's n plus. You will see for the next one, it's n minus. So S naught is the value of the test statistic. So you have to calculate the probability where your test statistic is less than or equal to this observed value of the test statistic S naught when H naught is true. When given that H naught is true, that is, you have to consider the when H naught is true, we know S is having a binomial distribution, so you have to calculate the p-value using the binomial distribution, right? So this is what you have to do for the one-sided test when you calculate the p-value. So the next thing is how you are going to take your decision. Right, when you take the decision, we know after calculating the p-value, you can just reject H naught. You can reject H naught if your p-value is less than or equal to alpha. Right, if the p-value is less than or equal to alpha, you can reject H naught. So based on your decision, you can write the conclusion of your method, of your test. So these are the steps that you have to apply when it comes to the test statistic, right? Okay. So I think that is very clear when it comes to the non-parametric procedures, how to use the one sample sign test, right? How you use the one sample sign test, right? So Okay, now let's see the one sample sign test. Right, so I'll just copy all these things and explain you the next one as well. Right, so if you're going to test this alternative, that is if your H1 is m greater than m naught, right? I'll paste these things here. So when it comes to H naught, as I told you in the previous one, right? In this case also what you can do is, here you can write down your H naught as m is less than or equal to m naught, or you can keep it as m equal to m naught, whatever the way you'd like. So when it comes to the test statistic here, so the test statistic, so first you have to write down the test statistic. Right, when it comes to the test statistic here, we denote the test statistic again using capital S, and in this case it's equal to n minus. Right, so what is n minus? N minus is the number of negative differences in your sample. That is the number of negative differences in your sample, right? So when it comes to the p-value, again we are using this condition when H naught is true. Again the median is equal to m naught. So that is, we know we have, for the test statistic we can observe a binomial distribution. So the p-value is calculated using the same procedure, that is equal to probability, where your test statistic is less than or equal to the observed value of S, given that H naught is true. And then again you take the decision to reject H naught if the p-value is less than or equal to alpha. Right, so based on the decision you can take the conclusion. And then let's see how you are going to perform the two-sided test, right? When it comes to the two-sided test, that is your H naught is m equal to m naught, H1 is m not equal to m naught. So in such cases, how we are going to perform the test? So in that case also you have to write down the test statistic and what is your p-value and how you take the decision. I'll just take a copy from the previous one. Okay, I'll show you. Right, now when it comes to the two-sided test, right, it's a bit different how you calculate your test statistics. So in that case you have to calculate n minus and n plus both, right? You have to calculate n minus and n plus both, and what you have to do is you have to consider the minimum value from n minus and n plus, right? So in this case this is n plus, so you take the minimum value from n minus, and you calculate the n minus and n plus, and you take the minimum value among them as per your test statistic. And again when you take the p-value, right, where you know when H naught is true we have this binomial distribution, so you calculate this probability, and since this is a two-sided test you have to multiply this by 2 to calculate the p-value, right? And then the decision we take using the same manner, that is we reject H naught if p-value is less than or equal to alpha. So I think you're clear with the procedure. right? So I think you are clear with the procedure. So I will explain you one example, right? I will explain you one example. Okay. Another thing I have to tell you is, now I told you when you are applying this sign test, the variable of interest should be in the continuous scale. So that is when you are taking the difference between the observed value and the variable, it cannot be equal to 0. But sometimes based on our values in our data set, it's been equal to 0. So what you have to do is, in such cases, we have to omit that observation and then we have to adjust our sample size accordingly. I will explain that using an example, right? First, if you look at example 1, you can see for a sample of 11 students, time taken to answer an MCQ question, you have a sample, that is they have taken 11 students and they have checked the time that is taken by each student to answer an MCQ question. So can we conclude at the 0.05 level of significance that the median time taken by a student in the population from which the data were drawn is different from 3.5 minutes? So what you have to do first is, you have to read the question and check whether the assumptions are satisfied to apply the one-sided sign test, one sample sign test, right? So you can see here the variable is time and it's a continuous variable, right? And it's the scale is also satisfied, right? It's higher than ordinal scale. And the next thing that you have to check is whether the observations are independent. So you have the students here. So the students' observations are independent from each other. So all the assumptions are satisfied. So because of that, we can go to non-parametric method. So first thing, we have to set the hypothesis. Now they are asking us to check whether the median is equal to 3.5. So that is, this is a two-sided test where you have to test m equal to 3.5 versus you have to check, I'll take the alternative as h1, m is not equal to 3.5. So this is the hypothesis. Now hypothesis is done. So now how we are going to calculate the test statistic? So I'll take this table here. I'll just copy the table. And when it comes to the two-sided test, I told you when you calculate the test statistic capital S, that is the minimum from n plus and n minus. So here you have to calculate the difference. So you can see when you calculate the difference, so that is observed, the difference is you have to calculate the observed value minus 3.5, the testing value of the median. So that is 1.8 minus 3.5. You have to just put the sign. So 1.8 minus 3.5, it's a negative figure. So 3.3 minus 3.5, negative. This is positive, negative, negative. This is equal to 0. And here negative, 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 this negative and negative, right? So you can see you have one observation where the difference is equal to 0. So what you have to do is, you have to actually omit this observation from your sample. So at the beginning we have 11 observations. Since we are going to omit this, now we are having only 10 values in the sample, right? So what we have to do is, if you take the n plus value, right? If you take the n plus value here, So if you take n plus here, I just write n plus, right? So that is the number of positive differences. So how many positive differences you have here? We have only one positive differences, right? So n plus would be equal to 1. And if you take the number of negative differences, that is n minus, right? So I'll take it here. So number of negative differences 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 number of negative differences. So n minus would be 9. So when it comes to the test statistic capital S, that is equal to the minimum from, this is equal to minimum value of 9 and 1. So that is equal to 1. So now we know our test statistic. Now we have to calculate the p-value. So when you calculate the p-value, so the p-value is equal to, so the p-value is equal to, you have to calculate the probability where our test statistic capital S is less than or equal to the observed value of the test statistic. So here the observed value is 1, right? Observed value is 1, and given that, right, observed value is 1, given that it's coming from H naught is true, right? So when H naught is true, we know it's coming from a, it's when H naught is true, okay, wait, this should be equal to 1, this should be equal to, this should be equal to 1, and here if you take the test status when H naught is true, we know S is having a binomial distribution, but now our sample size is equal to 10 because we omit one data point and the probability is 0.5. So now we have to read the value. Since it's having a binomial distribution, this is where you have to read the binomial table. So the binomial table is also uploaded for Cal, right? So I will show you the binomial distribution, the table of the binomial distribution.
No.
Right, now this is the binomial distribution. Right, this is the binomial distribution. Right, so what you have to do is you have to take this cumulative binomial table, and since our sample size is 10, see in the first column you have the sample size, so you have referred to 10, right? And here you have sample size equal to 10, and you can see in this row, you have the probability of a success. So here our probability of success is 0.5, and the x value, that is the observed value of our test statistic. So in our case, the observed value of the test statistic is 1. So you have to read 1 from here, right? So that the corresponding probability value is this one, 0.0107. So you have to take that one when you calculate the p-value. So since this is a two-sided one, you have to multiply this, you have to multiply this probability value by 2. Right, you have to multiply the probability value by 2. So that is from the table we have 0.0107. So you have to multiply that by 2, where you have 0.214. 0.214. 0.0214. So that is the p-value. Now you can take the decision, that is, since our p-value, that is 0.0 approximately 0.02, this is less than 0.05, so we can reject H naught, right? So the conclusion is, if you are rejecting H naught, the median time taken by a student is not equal to 3.5. So you can write the conclusion as well. So this is how we perform the one sample sign test. I hope all the steps and everything is clear. So there's another example that I have mentioned in my lecture notes. So I want you to try with this example and come when you're coming for the next session, right? Give a try and give a try and calculate the value. So we'll be discussing this question. I will be discussing this question in the next case, right? Okay, thank you so much for coming, and I hope you understood everything, right? I hope that you understood everything, and we'll be explaining this the example in the next session. Thank you so much.